Okay, so hey guys, I am recording now, and do let me know if it stops at any time. The recording stops at any time. So yeah, let us get started. Okay, so hey everyone, welcome to Let's Talk, um, the Let's Talk event for SIG AI. And today's topic is going to be supervised learning. And if you have may noticed, I have changed the topic to part one instead of um, classification models. So I'll let you know about that in a bit. So I'm Bharadwaj, firstly, and I'm your host today. I am a junior here at UC Merced, and I'm a computer science and engineering major and a cognitive science minor. That's my Discord over there. Do like text me if you have any questions on AI or any tips that you want to give me, or like just talk in general. Yeah, the Discord's right there. This is Hyro, and that's his Discord. He's also one of the co-SIG leads for SIG AI. And yeah, that's him. And he handles the Let's Code events. So what exactly is Let's Talk for the guys who are joining us for the first time today? Let's Talk and Let's Code are two different events, and a series of events that SIG AI is conducting. And what we do is at SIG AI, we feel like it's a place to learn something new and a place to throw your fears away from speaking. So I really encourage you guys to come and speak. Turn on your microphone. We'll be having lots of discussions in this workshop. So do turn on your microphone, and I'll be asking you questions, and you guys can start talking. And this place is not somewhere where I come in and start talking about everything, because I myself don't know everything, and it would be really nice for if you have something that you would share that maybe I might have not known. It's some place where I can learn something too. So it's a place where we all can share knowledge, and all of us can gain knowledge. So yeah, hopefully today we're gonna have a good event. So if you take a look at the QR code here, just feel free to scan it now. So this is the workshop schedule for the upcoming events for Let's Talk and Let's Code. So you may be asking us, why are you giving us the schedule, like, right? It's just to help you guys to know what's coming up. Maybe you can learn something on your own and come here and talk about it. Maybe you have something else to share that you really found interesting. So you can share it with us too in the Let's Talk events. And it's totally fine if you're completely unfamiliar with something, and don't feel insecure about it. You can ask questions whenever you want, and this is the place where we all are learning. Yep. Okay. So let's begin. Today's topic is going to be it's going to be a mixture of classification and regression models. Not too much on the regression models, but classification. You'll get to know more about that later. But we'll start off with a recap for the people who didn't attend our previous workshop, where we talked about an introduction to artificial intelligence and machine learning. Then we'll go on to what supervised machine learning is, the types of models, regression versus classification models, linear regression, binary and multi-class classification, logistic regression, support vector machines, and then questions. As you see here, we didn't include the naive Bayes algorithm. It's because we may run out of time. I wanted to include linear regression in this so that we'll have a good flow through the whole workshop. But yeah, I did link the resource for naive Bayes algorithm. So yeah, go do check it out. It's on our SIG um, SIG AI's Discord. So do check it out. Okay, so let's start with the recap. So from the last workshop, does anyone remember what AI is? What is AI basically? Does anyone remember? Just unmute and
Artificial intelligence.
yes, yes, correct. A beautiful answer. I like that. But can you elaborate on that a little bit? What exactly do you think artificial intelligence? It doesn't have to be right. Like it's what you think. What artificial intelligence is.
Pretty much like automated systems, we could say that, or automated machines.
Uh-huh. Yeah. Automated machines. Okay. And anyone else? Anyone else? Please do unmute.
If I remember correctly, I think
Mhm.
the term we said was like teaching like machines how to make decisions based off data,
Yes.
right?
Yes. Correct. Yep. That is exactly what our AI is. So AI is nothing but enabling machines to think, which is what exactly you said, and to think to reach a final goal, right? So we want the machine to do its own task without any intervention of human beings. So having an intelligence on its own, of its own. So that is basically what AI is. These are the key points that you have to remember whenever you're talking about AI. And an example of AI is self-driving cars, right? You just let the AI do its thing. Like you don't interfere in it. Okay, so that is basically what AI is. And do you guys remember what machine learning is? AI and machine learning. The difference between AI and machine learning. I think it's already on the screen. If you guys are good at reading, then you guys can say it really fast.
Uh, well, I think for like machine learning, you don't need like specific programming for it because it'll learn on its own based on the data you give it.
Mm-hmm. Well, that is partially correct, but let me correct you on this. So, machine learning is basically a subset of AI, where you use some statistical methods, which enable you to improve your model. So, artificial intelligence is, in simple terms, a machine on its own, and interacting with its environment and trying to make decisions on its own. But machine learning uses some statistical methods as well, but with a little bit of human intervention, with labels and stuff. It goes really deep with deep learning and stuff, and we'll get to that in the coming Let's Talk events. So, and we also talked about data science. If you guys remember, data science is a is a subset of these three big sets, which is if you guys can see my pointer, I don't know if you can. Okay, yeah. So math and statistics, computer science, and subject matter expertise. It's it's the intersection of all these big sets, and data science sits right in the middle. And as you see here, the intersection of mathematics and computer science is machine learning, and the intersection of math and statistics and subject matter expertise, can be any subject, is research, and the intersection of computer science and subject matter expertise is software. Yep. Okay, so if you guys remember, we also talked about the three different machine learning models in the last Let's Talk event, which was supervised machine learning, unsupervised machine learning, and reinforcement learning. So, question to you guys now: what do you guys think is supervised machine learning? If you guys remember, do you guys remember? Like, well, what is supervised machine learning? If you guys want a hint from the last time, this was the picture that we had before. So yeah, go ahead.
Isn't it when you give the your model like a training data set,
Mm-hmm. Mm-hmm.
and then your model starts learning from it and starts getting more accurate and more accurate?
Yeah, bingo. You hit the nail. So basically, supervised machine learning involves giving the model data and specifically labeled data. So this is a really key important point here. Whenever you give the model labeled data, it's able to predict whatsoever you want it to predict with the data that you give it. For example, here, if you give a data set with height and weight, and you ask the model to predict if a person is obese or not, with past labeled data, it's able to predict the output using various models. So this is supervised machine learning. And okay, so this is what we're going to cover today. We're going to cover linear regression, and in classification models, we're going to cover logistic regression and support vector machines. Okay, so let's go. Okay, so does anyone know the difference between regression and classification problems? Does anyone know the difference between regression and classification models? Anyone?
I think it's the regression is predicting like a specific value, and then classification is assigning some sort of like category, like a binary category to something.
Correct. Yeah. That is exactly right. But for classification, it may not always be binary. So let me repeat what Dylan said. Is it Dylan? Did I spell it right?
Yeah.
Okay. So a regression is, what I like to think of it is giving a number output, basically. So you're, for example, here you have a question, right? What is the temperature going to be tomorrow? You're expecting a number output. So your prediction will be a number. That's basic. You use a regression. This is basically a regression problem statement here. And a classification problem, on the other hand, is grouping. May not be binary, where we classify into two different categories, but it can also be a multi-class classification problem, which we will talk about in this Let's Talk event soon. So a question or a problem statement for a classification problem would be, will it be cold or hot tomorrow? Which you can see here. So you're classifying, right? You're putting it into groups.
So what you're saying is that classification gives you more like probability, while regression gives you like a prediction?
Probability to tell if something is true or false, or and a regression. See, if it gets kind of complicated there, we're going to talk about that today. But when you say that you want a probability of something, then it can be a regression problem. But if you're taking the probability and giving an output out of it, let's say you have a probability that today is going to be 90% cold, 90% cold and 10% hot, then it becomes a classification problem. You get it? So it's based on the output of what you want.
Yeah. So just a little bit, but I guess we'll get it as we go on.
Yeah, sure. Yep. Okay. Next. So we're going to first talk about linear regression, because to understand logistic regression, we need to understand linear regression first. So linear regression is basically a model that, let's say you have some data, right? You have some data plotted out in a graph, and any type of data that you have that's plotted in a graph, and then you want to estimate. Let's say you want to estimate something. Then you for linear regression, you need a best line of fit. Now, what is this best line of fit? This best line of fit is actually a line that is able to line itself exactly to the points where there's less distance from each point. So let me give you an example here, right? Okay, now let's say you're going to buy a house, right? And you want to buy a house really next to some good amenities, right? Let's say there's a hospital here. If you can see my marker, let's say there's a hospital here, right? Hospital is really important. Maybe a grocery store, right? There's a grocery store over here. And let's say you have a school, right? Maybe you go to school. So there's like a school over here, right? So now where would you buy a house, right? If these three amenities are really important for you, you wouldn't buy a house somewhere over here, right? You wouldn't buy a house there, or you wouldn't buy a house somewhere over here. Let's just assume that these are the only amenities that are available in the whole city, and this is the city you want to move into. You wouldn't move somewhere away, right? You would, your main goal is to move somewhere that is close to these amenities, maybe equidistant to each of these points or each of these amenities, right? That's exactly what linear regression is doing. We can use the same analogy here to think that each of these points on the line is where you can find a house for you. And these dots over here, you can take them as amenities, right? So the distance will be the shortest distance away, and this line is always always fitted to where it averages out the lines from the dots. Okay, so let's say there's some problems with linear regression though. Let's say there is some outlier somewhere over here, right? Maybe there's some amenity here that you really want, right? So what the linear regression model does is it says, oh, I need to find, I need to take into consideration this point as well. So what this does is it starts averaging out over here. The line moves down, not exactly here, but somewhere around there, right? Just to average out that point, because it has to take each and every point into consideration. This is the problem with linear regression. We can't we can't get a really accurate best line fit each and every time. If sometimes you might have some exceptions that you have a point here, point there, right? And it has to take into consideration all these points, and these can mess up the best line of fit. So that's why we're moving into these other types of classification models, which is logistic regression, which we will learn about. This is where you'll get all your answers to how we're going to deal with this problem of outlining of these outliers. So
the question.
Mm-hmm.
Oh, so do you call the distance between the linear line and the data points as
Yes.
noise?
Yes.
Okay.
Mm-hmm.
Yeah, just to make sure.
Yep. Mm-hmm. Okay. So classification models. Okay, we will get to this question later. But to get to this question, I need to explain you guys some of these key terms here. So remember, we were talking about binary classification and multi-class classification, right? These were the two types of classification techniques. So binary classification is nothing but these two classes here, right? You're separating two classes with one line, or right? Multi-class classification models separate them into more than two groups, like here. I really want to explain you guys more, but this picture that I found online just explains you guys everything. So binary classification into two groups, multi-class classification, more than two groups. An example for that, if you guys remember, was from the iris data set. From the iris example that we were talking about, iris flowers example, where we had three types of irises: setosa, versicolor, and I forget the last kind. But we use that to classify them into more than two categories. So let's move on to logistic regression. So logistic regression is a binary classification problem statement. So we're classifying it into two different groups. Here, the data. Okay, so excuse me. The only difference between logistic regression and linear regression is that logistic regression fits an S-shaped logistic function. So it's not a line here. But in linear regression, it's a best line of fit. So and as you see here, the S-shaped logistic function is the green line, that you see over here. And this is trying to find the function that best fits this data points. And and the red points here are the false samples, and the blue points here are the true samples. We'll get to know more about this in the next slide. So why is it even called regression when it's like why is it even named logistic regression in the first place when it's a classification model, right? It's called regression because it's similar to linear regression. I know it's silly, but that's how it uses really similar methods to how it classifies the data. That's why it's called logistic regression. And sorry, regression. And it's called logistic because we're using a logistic function. So we're using a logistic function here. It's an S-shaped curve. It's an S-shaped sigmoid function. And it usually doesn't measure something that's like continuous, like body weight or size, body weight and size. But what it usually does is we use logistic regression to say if something is either true or either false. And how much of true or false it is what matters. So we'll get to an example, so you'll get a better understanding of how logistic regression works. Okay, so here, logistic regression, we're taking an example of to find if a mouse is obese or not. Okay, so here we want to classify mice if they're obese or not. That's the whole point of this example. Over here, wait, let me see if I have my pen. Okay, so over here are the mice that are obese, represented over here. And here are the mice who are not obese. This is the data that we have. So usually what a logistic regression model would do is it would try to find the best fit to the data by maybe drawing a line like this, right? But this becomes a problem because sometimes if you classify the data like this, you might have a mouse over here that may not be obese, but it's still classified as obese. And you may have another mouse that is obese, but is still classified as a not obese mouse. So instead of linear regression fitting a line, logistic regression fits an S-shaped sigmoid function. And we'll get to know what this S-shaped sigmoid function is doing. So this curve, this sigmoid function, goes from 0 to 1. And as you said, I think, Christian, was that you? You were talking about probability before, right? So So this curve tells you the probability of if a mouse is obese based on its weight. Okay, so this curve is basically the probability of it. I'll explain it in the next slide. So let's say we have a mouse that's really heavy, right? Okay, so maybe he's over here, right? Let's say a mouse is really heavy. Then there's a high probability, there's a really high probability over here that the mouse is obese, right? But let's say we have an intermediate mouse over here, right? We have an intermediate mouse. Then there's only a 50% chance, or the probability is only 50% that the mouse is obese or not, right? And let's say we have a light mouse over here, right? There is 100%, we know 100% that the mouse is not obese. If we have a mouse, if you have a mouse that's weight is around here, right? So this is basically what logistic regression is. We're able to get the probability if a mouse is obese or not, and this is generally how we use it in classification. So all logistic regression does is it tries to plot a sigmoid function where it's able to tell if a given data point, or if a given mouse in this example is obese or not. So it's only binary here. Okay. Logistic regression can also be done in multi-class classification models. But it goes into too much detail in mathematics that I don't think we have the time for today. But do let me know if you want to learn that. So we'll maybe get another Let's Talk event soon on that. Okay. Yeah. So basically, bottom line is that if the probability that the mouse is obese is greater than 50, then we'll classify it as obese anyway, right? Else we'll classify if it's not obese. That's all logistic regression is doing. And in this example, that's the best way to remember it. Okay, so next we'll move on to support vector machines. Now, support vector machines are kind of similar to linear regression, but not as much. So we'll see how they're similar. So if you remember, linear regression was finding the best line of fit with the data points that was given to us, right? For the data that was given to us with different features, right? But support vector machines here, excuse me. Firstly, support vector machines are both classification and regression models. So you can use this support vector machine in both classification problems and regression problems. And as you see in the coming Let's Talk events, you'll realize that some of these models can be used in both classification and regression problems, both. And also support vector machines, as I said, try to find the best line of fit, but they do it in a little different way. So let's see how they do that, right? So there's some key things that you guys should understand here for support vector machines. And these are some key terms that you have to remember. They're all interlinked. So let me explain it to you step by step. So firstly, these lines over here, I don't know if you can see my cursor, but let me use a pointer now. Okay, so these three lines over here are known as hyperplanes. They look like lines, and they are lines here, but we like to call them hyperplanes. I'll tell you why later on. You'll get to know why we call them hyperplanes later on. So basically, in linear regression, our goal was to find this best line of fit, and it tries to adjust itself with all the points taken into consideration, right? But what support vector machine does differently is that it takes two more hyperplanes. As you see these dotted lines at 1 and 2. These are the two other hyperplanes it uses as it uses to find the third hyperplane. And I'll tell you how these 1 and 2 hyperplanes are even here. Okay, so so what are support vectors basically? Support vectors are nothing but these points over here. Okay, so what these other two hyperplanes, these two dotted lines, what they're doing is they're using these support vectors as support, basically. So they're called support vectors because these hyperplanes pass through them. These marginal hyperplanes are drawn passing through these support vectors, and they're drawn such that there is a maximum distance between these two hyperplanes, which is called the best margin. Okay, we always want to maximize this marginal distance, and that is how we are able to estimate where our best fit line exists. And we can try to calculate this best fit line by passing by passing hyperplane 1 and hyperplane 2 through these vectors. So and this hyperplane in the middle is called the dividing hyperplane, and this hyperplane is used for our estimations. So basically, you see here that it's really easy for us to like just draw a line between the points, and draw some marginal hyperplanes, which are these dotted lines, right? And we're able to estimate the dividing hyperplane in the middle, right? Because these points are called linearly separable points. So linearly separable points are points where you can draw a straight line and separate them from each other, right? But there are some other things called non-linear points, right? That they cannot be separated by just a line. And so how are you going to separate them? Does anyone know? Like, can anyone guess? Looking at this one figure, right? Looking at number B, how do you think we can separate the non-linear points?
Like a non-linear function.
Okay, so how would you draw the non-linear function?
Could just be a circle for B.
Yeah, a circle, but how does the model come up with the circle? Like, there should be a way that the model comes up with that circle, right? Like for us, we can just see it and be like, oh yeah, I can draw this circle and group it away, right? But how does the model know? Like over here, what it's doing is it's trying to separate, it's trying to calculate the distance between each of them. It's able to tell between the different features, and it's able to draw a dividing line with support vectors and marginal hyperplanes. But how is it going to do it here? Because if it draws a straight line here, it's going to find two different classes, right? How is it going to see? Because it's only on 2D, it can't see more than that. I think I did already reveal the answer here, but the answer is what it does is it tries to look above it. So it right now it has only visibility of a 2D environment. There's something called an SVM kernel. What this does is that it increases the dimension to a 3-dimension. So okay, let me show you a picture here. So what it does is it converts the lower dimension to a higher dimension, like 2D to 3D. So it's able to classify these points easily. It'll make sense when you see the picture. So when you see this, you see it in 2D, it's really hard to separate it without a one line, without a linear function, right? But now, when you change the dimension to a 3-dimension with another feature, what it's able to do is it's able to get out these points and classify them easily. So it's able to now pass through a hyperplane between them. That is why we call these hyperplanes. Even though in 2D, when we looked at it here, even though in 2D it just looks like a line, we usually call them hyperplanes because support vector machines and their kernels usually use 3 dimensions, and their decision surface is where they predict the output to the model. So and anything above this will be considered an A class, and the other one will and the one below it will be considered a B class, whatever it classifies. So yeah, that was support vector machines, just in a really big gist. And wow, we went through it really quickly actually today, and we'll be having a lot of time for questions. So yeah, so these were the different machine learning models we covered today: linear regression, logistic regression, support vector machines. And the next time we'll be covering decision trees and random forests, which I think is the best types of models, which I really like. In fact, support vector machines, logistic regression, linear regression, we do use it a lot, but decision trees and random forests, I'll also be talking about something called AdaBoost and gradient boost, which you will realize it doesn't have a lot of overfitting. So let's talk about overfitting too, right? Overfitting is nothing but let's see this, right? Let's go back to this example. Okay, so do you guys remember this one point that I did over here and the outliers that I was talking about? So what this does, this linear regression model, is every time there is some outlier somewhere, it tries to move its best fit line to match those outliers, right? But and this is called overfitting. You're overfitting to the data because it's getting too used to the, like, whatever training data you gave it, it's getting used to that data so much that it's not able to predict the other another question properly. It's like, to understand this, it's like, let's say you're learning calculus for the first time and you only do 3 problems, right? And you only keep doing those 3 problems each and every time, and you're given a 4th problem and you don't know anything, right? it, that's basically overfitting. So you overfitted to those 3 problems, and you know only how to do those kind of 3 problems, but given another type of problem, you don't know how to do it. That's basically what overfitting is. And the best part about random forest and AdaBoost, especially AdaBoost, AdaBoost, Gradient Boost, and XG Boost, is that these these models, they don't overfit at all, and you'll know why in the coming Let's Talk events. So it's a really cool session to attend. If I were you, I would attend that 100%. So yeah, decision trees, random forests, we'll be covering that for the next Let's Talk event. And yeah, that's about it. It's really short today. Just covered 3 of these models, really simple models. And I will be linking you guys to some resources as well. Some really good resources that I would check out. Honestly, I would have loved to go over some of the math behind these terms, because I think you may have noticed today that it was not a little clear, just knowing the intuition part. So today, what I gave you was intuition of how these models are actually working, and how these models work on a high level. I really want to keep this Let's Talk event less technical, because I'd like you guys to come back even more. So yeah, sure, definitely. So yeah, let's. Oh yeah, so I lost my track there, but I think there's a lot of math behind this that you guys have to learn, and I will link those some videos that I learned myself to you guys. And if required, you can come back to me and ask me about these, the math behind all these kind of all these kind of support vector machines, logistic regression, linear regression, because this is how we learn how these models actually calculate these values. Like today, I just told you that, yeah, it calculates the best fit line, and it looks at the distance between these points, and it's able to calculate the best fit line. And you'll come back to me and say, okay, how, right? And I know you guys have so much confusion in this, and I'd love to explain it, but it'll get very complicated really fast. So that's why I'd like to link some resources, and I don't think 1 hour would be really enough to cover all this. So that's why I'd like to keep these Let's Talk events really high level. So it'll give you a push to learn more, and come back to these Let's Talk events and discuss how you guys learned something new, and what you guys learned from the previous Let's Talk event. So yeah, I will link some resources to these. Do look at the resources and come back to the Let's Talk event. We will have a 15-minute session to discuss about what we learned in the last Let's Talk event, which was this one. So like that, we will be able to remember what we learned before, and learn. Maybe some of us might have learned something new. Like maybe some of us might have learned the math behind it. So we would come and just talk about a gist of it, and then we can move on to our next topic. Excuse me. Right. So yeah, don't be afraid if you guys were kind of like going around not understanding some of the things, because such things can't be understood in, like, just 15 minutes. I just went over it in a very high level, but yeah, I will link the resources. Do check it out. This is more of a pusher for you guys to go start learning, because it's really easy. As you see here, it's as easy as I explained it to you guys, just drawing a line. That's all. So yeah, now I just like to open everyone for some questions, and yeah, and thank you guys so much. Please do check out this QR code here. This is the link to our next upcoming events, so you can scan it over there. Yeah, so now for the questions. Thank you so much for joining us today. It's been a pleasure. Yeah, cool. Oh, and I think Hyro has joined. Yeah.
Yeah, what's up?
Hi,
Sorry for
Hyro.
being late, but I'm here and really nice talk. I really liked it.
Yeah. Thank you so
Yeah.
much. Okay, so we'll open it for any questions, guys. If you guys have any questions, please do ask now. That would be a great time.
Yeah, Brad.